Hallo, mein Name ist Jens Gutfleisch von der Filmkommission Region Stuttgart. Und es ist wunderbar, dass so viele Leute wieder den Weg hierher gefunden haben. Ganz toll. Ansonsten begrüße ich jetzt ganz herzlich Dr. Arellano und mit dem Thema Machine Learning und darf Sie ganz geschwind nach vorne bitten. Viel Spaß heute Abend.
Okay, good. Thank you very much. My name is Diana Arellano, and I work at the Animationsinstitut at the Filmakademie as research associate. And today I'm going to give you an overview of what happens when machines learn. So I will start with a short story of what has happened to me during the past year. Whenever people ask me what I'm doing, basically I found these two phases. Either people are saying, wow, you are awesome, this is great, but many is like, okay, what are you doing? And many is just blank face. But I cannot blame anybody because this is a very difficult topic, but it's also very fascinating. So, what is machine learning? This is, besides to be a buzzword that nowadays everybody hears here and there, it's basically about teaching computers to learn in the same way that we do. And it means that they have to interpret the data in the world around us, they have to classify this data, and they also learn from successes and failures. So as you can see here in this image, artificial intelligence has been there for a long time. And then we have machine learning, that is a subset that deals with statistical methods to automate certain processes. And then we have deep learning, that it's a subfield inside machine learning that basically deals with or tries to simulate what neurons in the brain, how neurons in the brain work. And when you translate that to the computer, basically you have software, you write algorithms that what try to simulate is the behavior of all these neurons. So imagine we have in our brains all these little things interconnected and activating depending on what input we receive and giving some output. Well, that's exactly what we try to do when we write software that deals with what we call neural networks. So once we have that, how we can use it? So I chose this very simple example, and imagine that you want your computer to learn what is on this image, or to say if in this image, on this image you see a dog or not. So what you have here is you basically change this into all these pixels that you input to your network. And all these blue dots are nothing more than pixels that you give to the first layer of neurons. And here you can see that there are neurons that fire or they get activated if, for example, they recognize a line, or if they recognize some shape. And it's more than that. The neurons will get activated, for example, if they recognize some line on the upper corner of the pixel that you are presenting. So, and this is like the very basic stage. Then, when this neuron said, okay, I recognize something, I will give you my output. This output goes to the second layer. And the second layer, as you can see, it's a bit more specialized. So here the neurons will deal with, for example, is there fur, or what you are giving me, or what in the image can I see two eyes, and so on. And then it can go as deep as possible, therefore the name deep learning. And when you go until the end, then you can combine all these activation values, and then in the end you will get a result that is it a dog, yes or no? So this is very simple and very abstract. In reality, we are dealing with a lot of math behind. Everything is numbers, so you input numbers, you output numbers, and the way things get activated depends a lot of mathematical functions that actually will give you a better way, or will give your network a better way to learn, and a more efficient, of course. What would happen, for example, if we combine two things? On the one hand, we have some already trained neural network. This was created in 2012 at the University of Oxford, and you can see a lot of layers here. This network was trained to learn content in images using the largest database of images called ImageNet. This database has around 15 million labeled images. It took the people at the University of Stanford almost 3 years or over 3 years to get all this content. So when you have something like that, you can basically take it and use it in your program, let's say. So one example is style transferring. And this is nothing more than combine two images to obtain an image that has the content of one and the style of other. This is the work of Gattis and colleagues, very close here in Tübingen at the Vetre Lab. And what they found out is that this neural network that I just showed you not only is capable of recognizing content. So it doesn't just tell you here is a building or there is a river, even though you cannot see it, there's a river here, there are trees and so on. But the network could also tell you styles. No? So for example, I recognize colors, yellows, blues, blacks, and some shapes. And they found out which layers actually will give you that output. And what they did was to combine the specific layers and create a third image that would actually combine content, so for example, buildings, with styles. So for example, curves and colors. When we were experimenting with this using open source code, because of course now everybody is trying to contribute to deep learning, which is wonderful, and you can find a lot of material and very good code out there. And this particular example is fairly easy to implement. We started testing with this, and we decided to use something, some real artwork that was actually from a real painter, and we tried to apply it into the beautiful building of the Supercomputing Center in Vaihingen. And these are some examples that we obtained. Of course, this is with one set of parameters. The beauty and complexity of neural networks is that whenever you change something, imagine a dashboard with several knobs, and every time you open a knob or you change something, the whole thing changes. So if we would change some parameters, these results would be different. But it was not just us at the R&D department at Animationsinstitut who got very interested into that. It was also two of our students, technical directing students, who decided to take the whole thing a step forward. So they didn't just work with static images, they also used videos. And they did the same. They took footage, for example, from a current production called Paris You Got Me. And this particular student called Mahmoud Hesham decided to test how this would look like using this painting. And here you can see an example of one configuration of the network. So in the upper video, you can see what would happen or what happens when he told the network, okay, I want you to focus more on the content. And the lower video, you can see what happens when the network focuses more on the style. Now here you can see more stylization. Also the number of iterations. If you make the network go through the same set of data 3, 100, 1,000 times, of course, the learning is going to be better. Another student not only made his face stylized. This is Yurai Tomori on his third year of technical directing studies. He also took a trailer from the Aniplay 2017 called Pulse of Life, and he decided to stylize the whole film. So I won't show you the whole video, but if you visit our channel, YouTube channel, R&D, well, at the end is the list of all the links. But we have our R&D Animationsinstitut YouTube channel, and you can see all these videos there. In our case, we thought to deal with, or to work with animation. What would happen if we use machine learning to do motion synthesis? This is within the MSc project that is together with the HRM Supercomputing Center in Vaihingen and TKM. And the idea was to see or to explore how high performance computing, and in this case machine learning, could be used in some more in examples or in applications more film oriented. So one idea was to use it for animation. And these examples are from It's from the work of Daniel Holden at the University of Edinburgh, and we used it as the base for our work because what we wanted to do was not to use just human mocap data, but we wanted to use animated data to generate animation. So basically the approach that he uses is that he took several databases of human motion and he trained his network to learn to generate the locomotion. So the green skeleton is the one reproducing the exact data from the mocap data, from the mocap data set, and the yellow one is what the network actually learned. So as you can see, it's pretty similar. Many people would say, yeah, but what's the big deal? The network is basically copying the movement. Yes and no. It's really the network learned how to generate this motion by its own. And if the network can do this, then we can build on top of that and create or generate other type of motions. For example, in the, on the left, you can see that this is stylized motion. So using an extra database, like emotional movement, you can see what would be the result. So for example, the green one is a more tired, sad walk, the white one is more sad, and the yellow, I think, is the normal one. To test this network, we took a database of Thai dance, a very small one, and here we were not doing any training. What we were doing was to see if the network that already learned something could generalize and infer new motion. So in this case, you can see how indeed it did it. So the green one is the ground truth, so it's what it comes from the database, and the yellow one is a network generating the same motion. So again, you can see that you have something that you can actually use in your, for your own application. And something that really surprised us, and this is quite new, is that thanks to the support of Lux Studios, and they provided us with one clip of a walking cycle for a bird that's from the Manu film. And you can see here, this is the walking cycle and the skeleton, and the network actually, the model that we had, without being trained or anything, could reshape the skeleton. This is the human skeleton looking like the bird one, and simulating them or generating the motion. The yellow one, you can see, is not as good as you could have expected, but that's obvious because this network hasn't learned with this type of a skeleton and hasn't, even though it knows this walking motion, this skeleton is not what it knows. So if we would have enough data to train the network to learn this, then we would have a better bird walking motion. So this is the big deal about the whole thing. So we need data. So you don't do anything by creating sophisticated, beautiful algorithm or neural networks. You need a lot of data, and not just quantity, you need quality, you need good data, because the moment that you give bad data to your algorithm, it can either generalize or can get, for example, something that is called overfitted, that meaning that the algorithm doesn't really learn, and it learns very good all the samples that you give, but when you want to generate something new, it doesn't, and you start finding problems like this. Another thing that we are currently doing is trying to parallelize the code that we have. So this network that I just showed you, it's been trained, for example, in a GeForce GTX 1080. It takes around 7 hours to be trained. If we want to add more data and we want to do it again, of course, we will take perhaps a bit more, but what we want to do is to make it take less time to train. So that's what we are doing right now. We chose to do it on the GPU because the power that now, for example, the NVIDIA GPUs provide are very, it's huge, and we should take advantage of that. And it's also a way for us to, for example, use the cluster, the GPU cluster at the supercomputing center. So it's sort of all related, and that's where we are right now at the moment. I chose other two examples to motivate you to encourage you to see more the benefits of machine learning and deep learning into other film-oriented things. One is, for example, speech animation. This is a paper or the work from Disney Research and the Carnegie Mellon University that was recently published at SIGGRAPH 2017. And they address the problem of lip sync, so speech animation, and to how they could train a network that basically learns some speech and generates the animation, and that could be done in different characters. So this is very groundbreaking. The results are very good. Or, for example, the Watson system from IBM created a trailer from a movie on its own. And things like that are coming out. So I just hope I convinced you that deep learning is good. It's not just about robots killing people or cars just crashing on unexpected places. It's really fascinating field, and I just hope that more research is being done in this in the future. Here, some references. Thank you very much.